Hello. Inspired by Ben Iter's great video series about an 8-bit computer on breadboards, I built my own version and I made some enhancements to his build. In this video I want to tell about the enhancement I did to read from a battery buffered real-time clock and to access a micro SD card. Both of these devices are connected through an SPI bus, a serial peripheral interface bus, and I want to tell you how I managed to connect this bus to my system. I want to start with some general words about the serial peripheral interface, or SPI. So the main features of the SPI are there is a serial transfer of bits, so a byte is transferred bitwise, and the whole bus is host controlled. There is a single bus controller on an SPI bus, but there can be multiple clients addressed with this bus, so there are more than just one peripheral that is talking to the host or bus controller. There are many different device types available that have an SPI interface, whereas EEPROMs and SRAMs are the most common ones, but I don't use any of those. There are also sensors available like temperature or pressure and some more like smoke detectors and so on. So there are various different devices available. I have, as I mentioned in the intro, only an SD card connector and a real-time clock in my system, which are connected through this SPI bus. The first line that is part of that SPI bus is the serial clock line. That clock is always controller driven, so always part of the bus protocol is that the bus controller, that the host drives the clock. The host in this way tells the speed that the data is transferred. That is true for both directions, so as well for sending data as well as for receiving data. And there is one bit per tick that is transferred over the serial lines for each clock tick. There are two different clock states. This is the value of the clock line. The clock line may be idle or the clock line may be asserted, and both of these states are represented with either high or low value of the clock line. That means there are two possible clock polarities. So either idle clock is low, so that 0 volts or low value is when the clock is idle, or the idle clock may be high, that is called clock polarity 1. That is, the idle clock has the high value, mostly 5 volts, or sometimes lower values are allowed. There are two different data lines on the SPI bus, whereas the first line, COPI, this is the line that goes out of the controller out, CO, and goes into the peripheral, PI, that is for sending data from the controller to the peripheral. And the other line is called CIPO, that is the data line that goes from the peripheral to the controller. So that is whenever a bit is sent from the peripheral device to the controller. Both lines, data lines, are shared between all peripherals, so all peripherals send the data on the same data line. And since there are two data lines, in theory there is a full duplex capability, so data may be sent and received at the same time, but none of the cards that I use make use of that feature. As well as the clock has two different polarities, there are two possible data validities. So the question is, when is the data valid that is put on the bus? One possibility is the data is idle when the clock changes from idle to asserted. So that means whenever the clock changes on the first half, data is valid. So no matter if that if the clock idle is low or the clock idle is high, whenever the first change of the clock from idle to active or asserted takes place, the data should be read by either the peripheral or the controller. And the other possibility is the data is valid when the clock changes from the asserted to the idle state, or in the second half of a clock tick. That means the data should be read when the clock is falling for clock polarity 0, or when the clock is rising at clock polarity 1. So in total there are 4 different modes that are allowed for the SPI bus to operate, depending on the clock polarity, so whether the idle clock is low or the idle clock is high, and depending on the phase, whether the data is valid in the first half of the clock tick or the data is valid on the second half of the clock tick. Device, there is an additional line, the so-called chip select line, and there is one chip select line per device, and that line is active low. So whenever the chip select line for a peripheral device is low, that device is active and shall read the data that is sent on the data line, or that is required to send data back to the bus controller. And that means there is one line for each connected device. The more devices you have, the more lines you need to address those devices. If you have a host controller, you see that on the left-hand side, and that is talking to a single client. You see the clock line is driven through, as well as the two data lines and the chip select lines. That makes a total of 4 lines for a single client that is talking to a bus controller. And as soon as client comes into play, that client can be connected to the host, connecting the clock and data lines to the same connections that are used by the first client. An additional select line that selects the second client, and that means that the host needs an additional output for that client to enable. This is the schematic for my SPI controller board. On the right hand side you see the 2 breakout boards that I connected. This one is for the SD card connector and the other one is for the real-time clock. Of course, both cards are provided with ground and power. The chip select lines are held high by default with these 2 10K resistors. Otherwise, the cards might be selected during power up and might receive commands that destroy data. I especially had those troubles with the real-time clock before. You can see those select lines are connected to the 173 register chip that holds all the data that goes to the SPI bus. Besides the chip select lines, the register also holds the data outline and the clock line for the SPI bus. The register content is taken from the data bus while ignoring the upper 4 bits of the bus. Reading data from the bus into the register is done when the SPI write control line is active, which in turn is driven by the port controller that I covered in my video about the LCD display. The data line from the SD card and from the real-time clock are directly connected to this bus transceiver. I've chosen bit 7 to be the output bit on the data bus because the highest bit can easily be tested with the negative flag or might be shifted out into the C flag with a single left shift operation. The output is routed through as soon as the SPI enable line is active, which is also driven by the port controller. Since there is no other data from the SPI bus, I mirror back all the data from the register chip into the lower 4 bits. This transistor here, named Q1, is here to deselect the data line from the micro SD card as soon as the real-time clock is active. This is because of the problem I had with the breakout board for the SD card, which is always driving the output line high as soon as the breakout board has power. I have two devices connected to my board. The first one is an SD card breakout board, or more exactly a micro SD card board that holds micro SD cards, which in turn need a voltage level shifter. So since my CPU works with 5 volts, but an SD card requires 3.3 volts, there is a voltage level shifter that shifts down the voltage from my CPU down to 3.3 volts for the SD card. So also there is a bus transceiver on that board that is for the SPI bus to disconnect from the card if necessary, and otherwise all wires from the SD card that are required for the SPI bus are looped through so that there is no additional logic on that SD card, and the whole SPI peripheral integration, so the whole logic for the SPI bus operation, is placed into each and every micro SD card that you buy. So the protocol itself is handled by the SD card, and the SD card breakout board just puts the wiring through to the SD card. That board that I use has a design problem, and that problem is that although there is a bus transceiver integrated into the breakout board, the board drives the controller in and peripheral out line high, even if the breakout board is not enabled. So even though you don't want to talk with the SD card, that SD card drives the CIPO line high and thus blocks other client from sending data, because the host controller will always read a high bit from the data line. If you are an experienced solderer, you can easily correct that problem by disconnecting pin 13 of the bus transceiver U1 from the ground plate. So you just desolder pin 13 and lift that pin up, and then you connect pin 13 of U1 with the right hand side of the resistor R1, which is the client select line. And that means whenever the breakout board is disabled, the bus transceiver will disconnect the CIPO line from the bus. Since I'm everything but an experienced solderer, I add an additional transistor on my board that handles the same thing. That means as soon as the other card is activated, I will disconnect the CIPO line from the SPI bus. For the real-time clock, I use a breakout board for the chip DS3234, and that breakout board has a battery holder for a coin battery that powers the chip during the time that the CPU itself is powered off, so that the clock can tick forward even if the CPU is not yet used. Otherwise, all the lines from the chip are just looped through with this board, so there is no additional logic on the board. All the SPI interface is, and all the protocol is integrated into that chip DS3234. But there is an additional line on the chip, that is that square wave or interrupt or alarm output line, and that line signals whenever a certain time interval has passed. So you can program an alarm, or you can tell the board to inform every second or every tenth of a second. But I don't use that line in my design yet, but maybe later I could use it to switch between tasks at a certain time. Building that circuit only needs about half a breadboard. There is this RTC connector and that microcard connector. This is the transistor to disconnect the SD card from the register chip, and this is the bus transceiver to connect the data for the SD card or the RTC clock to the data bus. If I want to work with both devices at the same time on the same SPI bus, it's quite easy, because both devices have the highest bit first, so both devices expect to send and receive bit 7 of a byte first and bit 0 of a byte as last bit. And both devices work with a clock polarity of 0, so the idle clock is low. But the RTC chip, the real-time clock, expects that the data phase is in the second half of the clock pulse, while the SD card requires or expects the data to be valid in the first half of the clock tick. So that at first glance looks like I had to write two different read and write functions to operate with both devices, but I found out that configuring the real-time clock to polarity 0, so having the low value of the clock being the idle clock, allows both devices to read data that the controller sends if the data is valid during the whole time of a clock pulse, so that as well as on the rising as on the falling edge of the clock, the data is valid. And I can always surely read the data a few nanoseconds after the rising clock, so the data is already readable at the high state of the clock if I wait just a few nanoseconds after the rising edge. And so I can work with just one single function to receive and send bytes from the real-time clock and from the SD card. To receive a byte from the SPI bus, you have to keep in mind that the clock is driven by the controller. So this is the host of the SPI bus, even though the byte itself is sent from the peripheral. And the highest bit, the bit 7, is received first. So we start with bit 7 and we end with bit 0. And to receive a byte, you have to follow those steps. You set the clock line high, and then you read the bus from the CIPO line. Then shift that bit that you read from that line into your destination register just by shifting it into bit 0 and shifting all the other bits to the left. So the old bit 0 becomes bit 1 and so on. Then you set the clock line low again, get the clock down to idle, and repeat from step 1 until you have 8 bits received, which make a byte. This is the code to receive a byte from the SPI bus in my processor-specific assembly language, and the C register is the counter for the bits, and so I initialize that C register with the value of 8 so that I can count the bits, and then I initialize the A register with the current state of the SPI port, which contains all the bits that are unchanged, like the selected client that is sending the byte. And the loop itself contains as first the statement to set the clock high, so the clock bit is set and put out on the SPI bus so the clock gets high. And then I wait just a few microseconds and then read again from the SPI port so that the A register now contains the whole data on the SPI bus, and the bit 7 of that port contains the bit that the client sent. And with this command LSL, I shift out that highest bit into the C flag, and the LSL register B shifts that bit into the B register. So the bit 7 of the A register becomes the bit 0 of the B register, and all the bits that have already been in the B register are shifted to the left. Then I shift back the A register, and that statement clears the clock bit on the SPI bus, and so I reset the clock on the SPI bus. Last step is count the bits, so as long as there are bits to receive, I jump back to the receive loop so that the next bit can be read. After 8 bits are read, the B register contains the received byte, and this is moved over to the A register and then returned to the caller. To send a byte to the SPI bus, you also drive the clock by the controller, and you also send the highest bit, the bit 7, first. And you follow those steps. You shift a bit out of the send register. So in this case, you have to shift the send register to the left. That bit 7 gets shifted out, and the old bit 6 becomes bit 7 now, and so on. And the bit that you shifted out becomes the value of the controller out peripheral inline, so that is the data outline of the controller. Then you set the clock line high, wait a few nanoseconds, and set the clock line low again, so that during the whole clock pulse the data outline contained the valid bit. And then you repeat those 4 steps again until all 8 bits are sent to the peripheral. The code for sending a byte over the SPI bus also starts by initializing the C register with the value of 8, which is the number of bits to be sent, and the byte that should be sent is passed into that code in the A register. But the A register is the only register that can talk to the SPI bus, and so the value to be sent is handed over to the B register. The loop itself for sending all the bits starts by shifting out the highest bit of the B register, so the highest bit of the byte to be sent, into the C flag. And if the C flag is set, I also set the data outline of the SPI bus, and if the C flag is not set, I jump to this code where the outline is cleared, and then I put the data bit on the bus. I then add the clock tick to the bus, and a few microseconds later I reset the clock and put the reset clock out on the bus as well. And then I count the bits that are already sent and jump back to the beginning if there are still bits left to be sent. There are some things to consider during the initialization phase of the SPI bus. So there are some device-dependent things to keep in mind. The SD card, for example, needs at least 74 clock ticks before the card may be selected the first time. So you have to have 74 clock ticks before you set the client select line low. The real-time clock requires the serial clock to be low at the time that you select the real-time clock, because that configures the real-time clock to work with idle clock low, so with a clock polarity 0. There's also some device-dependent disablement. The SD card requires at least 8 clock ticks after the disablement, so that you have to send an additional byte after disabling the SD card. This is the code section about selection and deselection of a chip. So the chip 0, which is my SD card, is selected with this part of the code, so that the SPI port is red and the chip select line 0 addressing the SD card is set low and put back on the port. And this is the code section for enabling the real-time clock. It is similar to the one before, but of course there's another chip number which is set low, and also the clock, as mentioned before, is set to low, so that the RTC SPI bus is set in clock polarity 0, so idle clock is a low value. For deselecting the chips, I put all or both chip select lines high and put that back on the port, and then I sent an additional high byte on the bus, whereas the bits itself are not necessary, but there are 8 clock ticks that go on the bus, which is required by the SD card to disable. And this is the code for initializing the SPI bus interface on some of the cards. So first of all, I reset all clients. I deselect all the chips that are connected to the SPI bus, and then I send 20 bytes on the bus. 20 bytes by 8 bits, it's 160 ticks that are sent on the bus, and that should be enough, more than enough, because the SD card for now requires at least 74 ticks of the clock before enablement may be placed, but I sent a few more just to be certain. Okay, this concludes my video about the SPI bus. Actually, reading files from the SD card or reading the time out of the real-time clock might be an extra topic, but this video just covered the hardware aspects of the SPI bus. As always, feel free to comment, and yeah, see you soon. Bye.